Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 386, Moon Material Flammability. I'm Gary Jordan, and I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, and astronauts, all to let you know what's going on in the world of human spaceflight and more. NASA is paving the path for returning human presence to the moon and eventually to Mars. With that comes the need to understand as much as possible ahead of time on what life will be like and how to stay safe. You have your more apparent challenges to address, like a pressurized suit for working in vacuum, landing on the surface, and finalizing tools. But some of the seemingly smaller details can still present challenges. One of them is understanding flame behavior. Turns out that gravity may have some impact on flame size, intensity, and spread. In particular, lunar gravity turns out to be this Goldilocks zone that may prolong how long it may take for a flame to self-extinguish. Well, there just so happens to be an experiment that's an interesting blend of science with important knowledge that could translate to how to keep lunar astronauts safer. Joining us to discuss this topic is Emily Johnson and Dr. Paul Verkool, project manager and principal investigator, respectively, for the Flammability of Materials on the Moon, or FM² experiment. With that, let's ignite this conversation. Here we go.
T-minus 5 seconds and counting. 1. Mission start. T0. Launch commit light circle. Correct. Here she goes. Houston, we have a podcast.
Emily and Paul, thank you so much for coming on Houston. We have a podcast today.
Great to be here.
Yeah,
Thank you.
Thank you for having us.
All right. FM² is what we're going to be talking about, flames on the moon, and a lot about fire. This conversation is going to be fire. I'm sorry to kick off like that, but in the intro I did a pun. I have to start off with a pun, so this is the how we're going to get kicked off. Fires in space. Wonder how you got into the fields that you did. I like to start our conversations with all of our guests by learning a little bit about what got you to where you are. Emily, why don't you start? A little bit of biography that led you to become the project manager for this experiment.
Sure, yeah. So, NASA was not something that was ever really on my radar growing up. And when I got into college, I was studying molecular and cellular biology, and I still didn't really know that NASA did my particular type of science, but actually it was when Kate Rubins had her first flight to the ISS that I saw Kate Rubins, and she was, my particular type of scientist. And
Yeah.
I was like, wow, NASA wants people like me too. So after that, I applied for a couple of internships, and eventually I got into the Space Life Sciences training program based out of NASA Ames. And man, it just really changed my life. Honestly, that was where I fell in love with NASA, and it really kicked off my career. We've actually been able to start a similar program at NASA Glenn for physical sciences that's modeled off of that original program from Ames. And it's something we're super proud of, and the Ames folks are really involved in that too. So that's really cool. And after that internship, I came back to Ohio, and I got a job as a contractor for NASA Glenn, did some engineering work and did some ISS operations. And there was a civil servant program manager at the time who was just a really incredible leader. And she really inspired me to pursue leadership and management. And so that's how I got into project management. And now I'm the project manager for FM², and I get to help brilliant scientists like Paul, get their experiments going. And so, yeah, here, the rest is kind of history.
Yeah, and here we are talking about this awesome experiment. It's great to have you, Emily. All right, Paul, tell us about how you got to work with fires in space.
It was somewhat of a different path than Emily, starting from my college career at Case Western Reserve University in Cleveland. My college advisor, my undergraduate advisor, was Professor James Tian, and he actually was working with NASA. He was in a program doing research in combustion. And when it came time for me to graduate and look for a job, I stopped in his office and, basically getting ready to move on and get a job and career. But he said he had some work for me if I wanted to do graduate studies in the department, he had some work at NASA for me to do. So that's how I got my start. And I was very excited because I certainly liked the space program. Unlike you didn't have the advantage of remembering the first man on the moon and stuff, but I was actually alive. So I got to see that. So it very struck a chord that NASA was still a very, very a big deal for me at that time. Mm-hmm. So I was fortunate to get in the program. I immediately, this is actually in 1985, so it's been 40 years that I've been at NASA, and this might be today, could be the first day I actually started 40 years ago. I don't know the exact calendar, but it was right about the summertime. I was a summer student at this time, just after graduating undergrad, so it was right about the same time. But I started doing drop tower tests at NASA Glenn Research Center in combustion. So from the very beginning, I was doing combustion tests at the drop tower, and then it morphed, and of course, I furthered my career. I got my master's degree. Then I ended up, same deal. I was ready to move on. And he said, well, if you're interested in staying on, I got a PhD topic for you to work on. And we sort of made it work. And I was then doing modeling. So I modeled the test that I did earlier. So it all fit together and it all worked out. And then I got my doctoral degree. And then, again, similarly, there was an opportunity to work at NASA, which is kind of the way to get your foot in the door, start from doing some as a student researcher, kind of, and then moving up the ladder. So then I got to do additional experiments at NASA as essentially a real full-time employee, and that led into many combustion tests, both in drop towers, aircraft tests where we did zero gravity tests, and partial gravity tests. We actually did lunar tests and Martian G tests in the 90s because that was still of interest. And actually, one of my mentors at Glenn was Dr. Kurt Sacksteder. He was kind of the pioneer in that regard in setting up these partial gravity tests in combustion. So that was not us. They're talking 30 years ago now we did that. So this has always been an interest. And it took some vision. They saw the direction that we were moving. Generally, NASA's exploring, moving out to new worlds. So it's going to happen. We're going to go to worlds with different gravity. Yeah. So that's ultimately the interest and then the tie-in. So that's kind of how I got in the program, and I've been in the program now for 40 years. So.
Wow, yeah, long time. Definitely something you love if you stuck with it for sure. How did you make the migration from drop towers to combustion?
Well, actually, the drop towers we burned tests. We had a combustion chamber, so it was actually we dropped a chamber and we lit the samples during the drop. So it was a very small sample. We only had 5 seconds at NASA Glenn. The zero gravity facility is 5.2 seconds. So that you can do stuff. You can get zero G, of course, when you go into free fall. But at 5.2 seconds, this has to be usually a very small system so that keep the time scales short. So things can happen quickly enough to make meaningful measurements or observations in a very short time. So you can't burn a large piece of fuel, but you can do small pieces of fuel and actually get a lot of information from that.
I think this leads nicely into talking about fires in space too, because with the very limited opportunities on Earth, on the ground, obviously there may be some need to have more time to collect data and see how a fire spreads and propagates. So where can you find more time in the zero gravity environment than just the short amount of free fall that you get on Earth? No better place than in space.
Yeah, exactly. That's the ultimate goal. And that's when NASA has drop towers, because we can then do 5-second tests and then move on to aircraft where you have parabolic flight trajectories for airplanes that fly. Used to be the KC-135 in Houston. That's not here anymore, but that we get roughly 25 seconds of zero G. And then ultimately go to the space station where you have unlimited time. And that's why we do all the tests on the ground, which are limited in time, greatly limited in time and shape and size and all that. But it does give us a huge amount of information for developing these big flight experiments on a space station, which are very expensive and complicated. So we want to make sure we nail that. And that's why we do all these ground tests. And ultimately, when we get to the space station, then we have lots of time available to us.
Right. Being in public affairs, a lot of what we look for is a lot of imagery when it comes to trying to share with the world why, their science is so important in space and just fantastic and a very engaging thing. And more often than not, it's some of those combustion experiments on the space station that come up about, igniting some sample that burns in this very bright ball and then slowly extinguishes over time and creates little blue balls. It's very, very visually amazing and a good way to tell a story, at least from my side of this microphone.
Well, we appreciate that. Yeah, we have the fortune of being a very photogenic research area, where some people don't. I mean, if you're talking about protein crystal growth or something, it's maybe more difficult to show compelling images. Although obviously the research is compelling, but flames tend to be, people can connect with flames directly, so it makes it easier.
Well, why don't we go into that next? Why don't we talk about flames and what we know, and why is this a very interesting topic to explore, and why, when you take gravity away from the equation, that flames become interesting.
Well, to start from the most basic, what is a flame and what makes a flame, we often talk about the fire triangle, which are 3 legs of a chair or 3 points of a triangle that you need to get a flame to burn on Earth. It's basically you need fuel, you need oxygen, and you need an ignition source. So if you have those 3 components, then you can have, theoretically, you can have a flame. So we know on Earth that happens all the time. We don't even think about how often it happens on Earth. But of course, for example, pick a space vehicle like the ISS. So the International Space Station is a orbiting laboratory. As everybody knows, it's a very big laboratory. And it has, the most important part about that is that it has a large volume of oxygen, which the crew needs to breathe, of course. And consummate with that, you have a large amount of potential things that could burn. Anything from crew clothing to plastic bags that things are shipped in. So all of these things could potentially burn. So the only missing element then is the ignition source. So NASA goes to great lengths to reduce, eliminate, completely remove those ignition sources. But it is always a concern when you have an unintended fire that you have an accidental ignition source, and then it could lead to potentially having a fire. So that's what NASA is concerned about. And again, just because you have Earth, we have normal gravity on Earth, or the space station, we have 0 gravity. The elements are there for fire. But the gravity makes a difference in terms of how the oxygen is transported to the flame. So on Earth, because you have buoyancy, hot air tends to rise. And also, similarly, cold air kind of falls. If you have a look at a candle flame, the hot air is rising upward, but replacing that at the base of the flame is cold air coming in. And that is fresh oxygen that the flame needs to sustain itself. So you could think, well, if you go to 0 gravity, that mechanism goes away. You no longer have any reason for, there is no up or down. And perhaps people have seen some candle flames in 0 gravity. It looks like a small blue ball burning. And yeah, there is no up or down. But there is a flow. If you have airflow on a space station, you have circulation to keep the astronaut breathing fresh air. So there actually is a pretty significant circulation current. You could basically feel it blowing past your hands because of the air circulation. So because of that, on a space station, that serves as a transport mechanism for the oxygen. So not on Earth, just having oxygen is enough, but you also have to transport it to the flame. And on a space station, the way that happens is with circulation. So it's, again, you can have fires on a space station. And we're interested in figuring out the conditions in terms of the flow environment where the fire could occur. And then another important element is to what measures we take to minimize the chance of that happening if you do have a fire. So
a lot of what you're describing is very safety oriented.
Oh yes, that's definitely the application that we've always had for the research that we do. As NASA is interested in the very applied and important aspect of safety for the astronauts and the crew. And there, I don't know if you want to talk about. There's been incidents of fires in actually the Mir space station.
Yeah,
that was a pretty significant fire event on that. So that it's clearly a very could be very life-threatening, and so that's why we take it seriously.
Right.
So
yeah, here at the Johnson Space Center, very close to where we're sitting now, Building 9, they do training for the astronauts. Just if there is an ignition source and that smoke does start to build up in a mock-up, that the astronauts are well trained on exactly what to do in that scenario. So while you're looking at where can a flame come from? Are the astronauts safe? What are ways to mitigate flame resistance? The astronauts are training for, well, if there is a flame, then we kind of know what to do and how to deal with it and be safe anyway.
They were just doing that training when I was on the tour yesterday.
Oh, no way.
So that was a fun coincidence.
Yes, yeah. That's talks of flames being visual in terms of training. That's a very visual one because they actually introduce smoke into the mock-ups. It's very, very cool.
I should add, just beside the direct application that NASA is interested in, understanding how a flame behaves in 0 gravity is of vital scientific interest. So as a disconnected, fundamental investigation of the science of flames. That's what the research community is interested in. Going to zero gravity enables us to study things that we just can't do on Earth. So it leads to discoveries and, more importantly, model developments that we can't normally do on Earth. So we can develop sophisticated computer models from this research that we get, and then improve the computer models on Earth for other applications. So it's not just applied as far as NASA is concerned. That's their main interest. But the science community is benefited greatly from the research that we do.
Yeah, let's talk about some of the research that we have done in the past. I know, I've sat in Mission Control and done commentary for a number of Cygnus flights, right? And one of our favorites to talk about after a Cygnus is unberthed and released from the end of the robotic arm is the Sapphire experiment. It's one that we talked about a lot, and we talked about, how to tell the story, nothing better visual than some of the video from those Sapphire experiments. Do you mind talking about Sapphire and some of the other investigations that have occurred in space and maybe what we've learned from them?
Yeah, of course. Sapphire ended up being a total of 6 different investigations. So that, as you said, when a Cygnus undocks and then eventually burns up in the atmosphere, the idea was going way back that, I don't know if you know it or not, but the original plan was to set the entire vehicle on fire, the inside of it. But the vehicle owners did not like that idea, because not because they're going to lose a vehicle anyway on reentry, but there was a potential to lose control on reentry.
Oh yeah.
So they're trying to make sure that when they do the orbital deburning that they need to make it enter over the ocean so that it hits where it wants and avoids land, of course. So that was the only concern. That's the only reason we didn't actually do the entire, just like the vehicle inside, which would have been a wonderful full-scale test. We do this on Earth all the time. We have mock building fires. You've probably seen firefighters going, fighting a full-scale house fire, for example, for training. So that we could do that on Earth, and I think it was a good idea, but it just didn't pan out that we couldn't do the whole vehicle. But as a concession, we set up a large, I would say roughly refrigerator-sized test article where we could do large fuel samples. So that's what Sapphire ended up doing. So we burned large fabric samples, plastics, other materials, including Nomex that we burned, all, again, before re-entering the atmosphere. It was all automated, and we just, literally had the computer control which sample was burned. Some of them have multiple samples. One of the Sapphires had 9 different samples. More typically, some of them only had one big one. So it depends on a particular, whatever Sapphire mission it was. They changed quite a bit. And the nice thing was, for the first time, we actually got not only zero gravity combustion of a solid material, but a large scale combustion event, which we couldn't do on ISS typically because, again, safety reasons and other constraints. We really can't burn a 1 meter size piece of fabric, for example, easily on a space station. We just couldn't. Was not an option. But again, since Cygnus was unmanned and going to re-enter soon, that was something that we could do, and we got a lot of good information from that.
A scientist pushing the boundaries by every means, right? Let's light the whole spacecraft on fire. Yeah, but you want to do it for the sake of science. What does size have to do with what you can learn in terms of lighting a large sample? Why is that important?
Again, going back to NASA's practical interest in this, if we do have an unintended fire, in the unlikely event, hopefully this won't happen, but if we do, then you could imagine the fire is going to quickly get to be a large-scale event. So it's not going to be small samples that are candle size, and a fire, once it gets going, it's not going to be just a tiny flame burning. They tend to spread and grow. So that's basically again, for application reasons, we expect if we have an unintended fire and the flames get very big, it's a concern, because as we learned on Sapphire, once the flames get big, they almost get a life of their own in a sense, even though it's in zero gravity, because the flame is so large and it's a dynamic system. So there's fuel vapor being generated. It leaves the fuel surface, which is a velocity. So basically you have fuel jetting off the fuel surface, causes a puff to the flame. It also causes oxygen to come in. So again, it's almost like a living entity at that point. It's because as it's consuming fuel, when it's very large especially, it can actually it can generate its own flow to keep itself going. And we saw some of this with Sapphire. So again, it's just like the questions or the observations that we don't typically have that we got from Sapphire are that large-scale events could lead to unexpected outcomes for the flame, because we're just looking at small flames. But the large flames are different. They're very different. So that was kind of the reason.
Yeah.
Not all materials burn cleanly too. Like there are some materials that, as they're burning, they tend to kind of like come off in clumps, almost like little teardrops. And you can imagine that if you're in a microgravity or partial gravity environment, those little teardrops are basically turning into little fireballs that could float away and catch something else on fire. So understanding the different properties of the different materials at the different scales of flames is also incredibly important. Not every material burns the same way.
Yeah. It shows that you can't just ignite a very small sample in space and then call it good. No, you have to there's different ways that it could, because there's so many you don't really know, and it kind of adds to your general understanding the more that you do it and the more samples that you have. And repetition here is key. There's also been a number of other experiments, right? I mean, Sapphire is just one that I know that I've talked about before, but there's things called Lucy, Sophie, I think is another one. Do you want to talk about some of
over
those?
the years we've done quite a bit in combustion research. I should go back and say that Sapphire also did different oxygen concentrations, where the space station is air at 1 atmosphere, kind of what we're used to on Earth breathing. There is now talk of, as we move to other worlds and other habitats and even other vehicles, to increase the oxygen and decrease the pressure. So that was another parameter that Sapphire looked at. So we did some tests at higher oxygen and lower pressure. So that, again, for the first time, we got some data in potential exploration atmospheres, which NASA then is very interested in looking at, because, if you're going to build a vehicle in these conditions, here's what the flame looks like. And here's a whole new set of potential things you got to worry about. So that was just to finish that story.
Yeah.
But there's been many experiments that we've had to, over the years, have looked at combustion more recently. The Lucy experiment, which stands for Lunar Combustion Investigation, made use of a Blue Origin rocket, which for the first time, the Blue Origin was a sounding rocket, which means it basically just enters space and then comes back down to Earth. So we typically get approximately 2.5 or 3 minutes of zero gravity, and then the vehicle comes back down to Earth and lands pretty much right at the launch site. So unlike the space shuttle days, which actually go to orbit and then go around the Earth, this just goes up and down. So we get 2.5 minutes of zero gravity for a sounding rocket. But for the first time, and uniquely, in February of this year, Blue Origin did a launch where they spun the entire capsule to generate a centrifugal force. So the rotation rate of the vehicle was 11 RPMs. And at that rotation rate, we got a net centrifugal force at our experiment location of Lunar G. So it's the same as being on a merry-go-round, like in a playground. If you're on a merry-go-round, you spin it around, you're going to feel a force acting radially outward. That's a centrifugal force. And it serves as an analogy or a way to simulate lunar gravity if you go to interrotation. So for the first time, we actually did combustion test for extended duration at Lunar G in this rotating environment. And the results were very successful. We got some nice data. We burned a fabric sample, and we burned a plastic rod. And we just recently got the data back. Of course, we're going through the analysis, and very shortly we'll publish a paper on this. So we're looking forward to that.
Very exciting.
So that was a Lunar G experiment. And going back a few years, there's also another ISS experiment called SOFIE, which stands for Solid Fuel Investigation Experiment, where we're looking at burning different kinds of solid fuels, but now in zero gravity, but with a forced flow. As I said at the very beginning, the fire triangle is oxygen. You need oxygen, but in space you need to also transport that oxygen. So the way we do that for SOFIE is we had what we call a combustion tunnel. So it's a kind of like a wind tunnel. We put the sample in the wind tunnel and we blow air past it, and we've burned many different kinds of fuel samples. And there's been 5 investigators in the program, and got, again, lots of data. I would imagine if you did a search, you would find, as you talked about earlier, many compelling images from the flame test, because they do afford very nice pictures. But anyway, that's also another experiment that we've done looking at combustion.
There's a lot here, right? And here's the theme that I think leads nicely into our conversation about FM squared. Is a lot of the investigations that you talked about, except for Lucy, really had to do with understanding the microgravity environment. What happens to flames in microgravity, which can add to the context of what we know about flames in 1G. But changing the gravity equation and changing to, and maybe Lucy was the experiment that really led to this, is, hey, depending on the gravity, and you might have already known this from microgravity, is when you change the gravity, things change when it comes to flame behavior. Now, Emily, I remember us chatting a little bit before this conversation here, and you sort of described that the lunar environment, lunar gravity, is this Goldilocks zone. So hoping you can kick us off by sort of leading into this lunar component of flame behavior by describing what that is.
Yeah, absolutely. So when I first started working with the combustion team on some of these projects, I was trying to understand, these flame properties across the gravity spectrum. And someone had explained it to me that it's kind of like partial gravity is like the Goldilocks zone. Like in microgravity, the burn rate is a little too slow, and we get that nice, circular flame shape. And it's very hard for the flame to sustain itself without the flow that Paul has been talking about. And then, in 1G, the reason that a flame flickers is because that burn rate is a little bit too fast. But then when you go to partial G, like in lunar gravity, you'll notice that the flame is stable. The flame doesn't flicker, and it's because it's in that Goldilocks zone of that burn rate. And we expect the Mars environment to be similar, but obviously a little bit different. I don't know that we have a whole lot of Mars data, but that'll be something really exciting to look forward to as well.
Right. Yeah. So this is something that probably is of particular interest to scientists that are looking at combustion, right? Emily showed me some photographs of the actual experiment and the videos of them, and it was fascinating, right? Because at the other ends of the spectrum that she was describing in microgravity and 1G, the flames extinguished, but Lunar kept going. Was that on Lucy that you described, or is that a different experiment where you found...
That was the parabolic flight.
That was a parabolic flight,
yeah,
yes.
We had tested a fabric in it was the exact same conditions in 1G and then also in Lunar G on the parabolic flight. Mm-hmm. And in 1G, the flame ignites, but it self-extinguishes pretty quickly. But in the Lunar G test, it ignites and it keeps burning. Mm-hmm. And that was, I think, the first time we've seen that behavior in this particular material, that it would extinguish in 1G, but it would keep burning in Lunar G.
Yeah, and as Emily said, that the Goldilocks zone, it ignites in 1G, but the flow is so high that there's a lot of cooling going on because the hotter rises. So the flame loses too much heat and it just goes out. But if you go to the reduced gravity, you have a little bit much slower flow leaving the flame, and it's actually the heat loss is less. So that's how the flame can survive in these conditions, by just reducing that flow speed a little bit and minimizing the heat losses. So was this I guess hypothesized before even lunar combustion experiments started, like, hey, we probably need to start doing investigations into this because we're thinking that it's going to be tough to extinguish, that these flames might not extinguish the way that we think. Yeah, definitely. In fact, going back to my undergraduate advisor, it was his theory that he postulated this way back when, looking at the data and saying, well, just kind of logically, if we think about it long enough, looking at 0G where things really burn very poorly unless you have flow, and 1G where things burn, well, there's got to, in between, what's going to happen in between? And he basically ended up theorizing that there's probably a point in between that's ideal or optimized for burning. So he postulated this way back when, in even 1980s. And the work we've been doing, experiments have sort of suggested this is the case in reality. So,
and here we are with this imagery that you showed me. It was absolutely fascinating to see some of this. Now the next steps, of course, are, okay, well, this is probably something that we should investigate, right? We're talking about returning humans to the moon. And of course, when they return, we want them to be safe, right, on the surface. So this is definitely an investigation that we want to understand. Enter FM squared. Emily, if you want to kick us off as to this experiment.
Sure. So yeah, FM squared will be sort of a follow-on experiment to, like Paul was saying, the last 20 or 30 years of these combustion science tests in microgravity and then leading into partial gravity. So FM squared will be a payload that will fly to the moon. We're hoping in summer of 2026. We're working with a commercial provider. We want to send 4 samples to the moon, and we're going to light them on fire and observe that behavior and try to figure out, where those samples will burn, and also when they don't burn. We're going to look at different oxygen concentrations and really try to map out what happens in real partial gravity.
So there's probably not a lot of, you want to send something to the moon, you have to think about payload size, you have to think about payload design, you have to think about making sure that wherever you put this payload, you're going to get the data that you want, which hopefully, fingers crossed, is video. Yes?
Yes.
All right. I'm very excited because that is, one of the perks about these kinds of physical sciences is the videos there. So when it comes to experiment design and how to design the facility and make sure it's going to get all the science that Dr. Fakul wants, how is the facility itself designed?
So we have an amazing engineering team working with us. They're from Sierra Lobo contracting company. Absolutely amazing team of engineers, and they have managed to come up with a hardware design that is actually capable of being used on multiple commercial providers.
Oh, cool.
So going forward, if we wanted to do another one, and we will, we can put this same hardware design on multiple providers and just swap the samples out. But the hardware consists of a combustion chamber with obviously sample holders in the middle and 2 cameras, an oxygen sensor, CO2 sensor, some temperature sensors to gather, different kinds of data. And essentially how the experiment is going to work is when it lands on the moon, it will already be pre-filled actually with the environment for the first test. So the igniter will kick off, sample will ignite, we'll collect the data. Then the chamber will vent to get that atmosphere out, all those combustion products out. The chamber will refill with the environment for the next test, and it will repeat that cycle 4 times.
Oh, and what are the different environments?
Different levels of oxygen. Paul, do you want to talk about that? Different ranges?
We're going to fill to different starting oxygen concentrations. Like one test, you might start at 30% oxygen, the next test at 25%. And the important thing here is, first of all, we will repeat these tests on Earth, and that will be our level of comparison. So we're going to duplicate exactly what we did on the moon and do it on Earth. And what we're going to see, besides the flame shape and structure being different, we're going to record oxygen during the burn. So because it's a unfortunate constraint that we have to be a very small volume. We don't have a lot of space because it's a commodity to go to the moon. It can't be a very big chamber. But the benefit is, as it burns, it's going to consume oxygen and naturally deplete the oxygen in the chamber. So at some point, it's going to go out, and we can record the oxygen that it goes out. So that's going to give us what you can call an extinction oxygen value. So if we say ignite a particular sample at 30% and then do it on the moon, it might go out at, say, 22%. It's going to consume some oxygen. So we record that, and then we can directly compare that to the test on Earth and see, does it also go out at 22%? We suspect not, based on what we believe. We think the moon, as we talked about earlier, could be the more dangerous in terms of flammability from oxygen point of view. So that's an immediate direct comparison that we can do from these tests.
Interesting. Multiple rounds, multiple samples, multiple environments. It gives you a lot of flexibility, but here's Paul over here wanting to get a big thing to light on fire as usual, but you gotta pick very, very specifically. So I'm sure a lot of thought has been put into, okay, well, here's the room that I'm giving with, here's the constraints that I'm giving with. If this is going to get a first go, here's what's important to me and the scientific community.
And timing of this experiment is really important too. We want to get this up on the moon as soon as possible and get that data collected so we can feed that back to future Artemis experiments. So we're really trying to get this on the moon before the Artemis 3 mission, before the first crewed lunar landing again.
So that would be important from a scientific perspective, a safety perspective, maybe both?
Yeah, both, for sure. Yeah.
Okay, very cool. So, well, great. Where are you guys now with the FM squared experiment? Hardware is in work, done?
Yeah.
I'm sure you guys are here in Houston for a reason, right?
Right. So hardware is currently being built. Yep, and we are on track to deliver the hardware next spring.
Cool.
Like I said, we're working with a commercial provider that will be launching. So, hardware is being built as we speak.
Very cool. And what are you guys doing in Houston?
I'm actually here for the NASA Next program.
Very cool.
It's a leadership training program, so that I've been here for the past week for that. And
Nice.
And I took advantage of the travel today to talk to some of the ISS folks that I've been working with over the years in operations and so on. So it was nice to connect. And
Yeah. And it's really good to have you guys here. So that's good. I mean, you guys are on track and a lot of work is being done. I'm very excited for future opportunities to get this tested. I wanted to kind of talk about the safety aspect of things now in terms of the timing of, like you said, Emily, you want to do this as soon as possible. But of course, we do want to turn it around and get something valuable, right? And of course, timelines for scientific experiments can be over lengthy periods of time to actually prep science and prep operations and procedures. So how do you plan to, are you already connected with the scientific community, with the Artemis community to make sure that this is on track or this is being monitored and people are aware and looking forward to what you have to share in terms of the results?
Well, the obvious, again, is because we're going to a different gravity level. That's the big question. Gravity changes. Well, how are things going to change for safety? But also, now that we're talking about having a human presence, extended human presence on the moon, where you could have people living for upwards of weeks at a time, they're going to be inside a habitat that's going to be filled to some oxygen concentration. So that's another question, is because there's actually reasons to have an environment that's higher oxygen but lower pressure, and has to do a lot with EVAs that the astronauts will be doing, or this it also has to do with the safety of the structure. So at lower pressure doesn't need as much of a material to maintain that pressure difference. But so there's reasons to go to higher oxygen, low pressure, but there's also definitely we know that it's going to increase flammability. So that's a concern. So we wanted these tests we're doing at FM squared will be at higher oxygens and lower pressures that are sort of envisioned. So that's part of it. So not just the lunar G aspect, which is of course the main reason, but also the actual in situ environments that we'll be looking at higher oxygen, lower pressure. And lastly, of course, going back to the fuel triangle is fuel. So what are we going to be burning? And that's where we're interacting with folks that are actually building these, or considering building these habitats. So what kind of fabrics, for example? Right now, we think a leading candidate might be something that's used for a typical, what's called a cargo transfer bag. So it's a kind of Nomex that's very common for moving hardware around. So that's a good representative fuel that we were considering burning as one of our samples, because that's going to be up there, and we're going to see how that actually burns on the moon compared to Earth. So that's pretty important, valuable data to get back from that.
Right. Yeah, and definitely something to consider, right? Those cargo transfer bags are tried and true materials, have been flown on the station, seem to be working fine. So use what you know for missions to the moon and see exactly what happens. So this will, I think, and Emily, you might correct me if I'm wrong, is this the first lunar surface flame test?
Yes, this will be the first ever flames on the lunar surface.
Very cool. It's been in lunar gravity, right, with the parabolic flights, with the Blue Origin flight with the centrifugal force, but this one actually on the lunar surface. So I think the scientific community is definitely looking forward to a lot of this. But you have a little bit of understanding of flames in the lunar environment based on the parabolic and centrifugal experiments that you've done. So you have some modeling, but this is really important. I think good to drive home is, you can only fly to the surface so many times and have a good understanding. And I think the flying, when you do actually fly, it lends nicely to how you analyze that data on the ground. And so, Paul, I'm sure that, whatever you learn on the surface really enhances the modeling, and that modeling can go a long way in terms of understanding the scientific value and the safety value that, you burn it once, sure, but it's all the work on the ground that actually leads to something valuable.
Yeah, it's an important piece. It's like putting it all together.
Yeah. So
it's not like sequential. You can't just say, we're going to do the modeling today, we'll go to the moon tomorrow, and then we'll go back to do something else. So it's a network, really. So one sort of bolsters and feeds on the other one. So the lunar tests that we're going to be getting will aid the modeling results that we get, which in turn the modeling can then help us to develop better tests to do in the future if we have opportunities to do additional testing. And that's always how it works with modeling. It's a very interactive process. That's why we always say modeling is is vital to any good research project, because you can get so much with experimental data, but then like after FM squared is completed, that was a tremendous opportunity, but it's what then? So what we still on Earth we can make benefit of that data and develop the model and strengthen the model, and then actually predict what will happen in other cases that are similar, and then ultimately again produce even more, or produce other experiments that give us additional data that we're missing. And again, it sort of feeds back and forth, and they bolster each other.
Yeah. And one of the reasons that it's so important for us to have FM squared on the lunar surface is that a lot of our ground analog facilities, either a parabolic flight or a drop tower, to get simulated partial gravity, we have to use a centrifuge most of the time. And in the parabolic flights, there's G jitter. Essentially, these ground facilities and the way that we simulate partial gravity here on Earth is not perfect. And in order to get the best quality data to feed into those models to have the most accurate results possible when we're talking about astronaut safety, right, we really do need to go to the lunar surface to collect some of that data.
Yeah, that gives the benchmark. I mean, that's what the reality is. So we need to know what that is to develop the models. Yeah.
Very, very important. And I'm sure you guys are pretty excited to, you said like next spring you could be ready. So that's not too far away. So it's got to be an exciting time for the community to actually get this going and see FM squared, hopefully fly very soon.
Yeah, absolutely. We are so proud of this and so excited for it. I think this just goes to show there's a lot more work that needs to be done in this area of study. And we did just get approval to build a follow-on FM squared payload. So looking forward to that as well. There's plenty more to come here, and we're very excited for it.
Plenty more to do. That's right.
Yeah, it's pretty exciting. And as Emily said, we have a very, a capable team and a pretty sizable team. And we couldn't do anything without the guys. They're doing the engineering and the research for analysis for us. But, getting to think about this experiment, it's as Emily said earlier, the first time we're going to be using fire on another world in a manner that humans are used to using fire. So archaeologically, I think I looked up the date that people think that we use fire on Earth first for whatever cooking or tool making or whatever, and it's roughly 800,000 years ago. So nearly 1 million years ago, they deduced that's when people started to use fire. So we don't know the exact date, but we will know when FM squared flies. We will know the date that we do a fire in an environment like people are used to burning for the first time on another world. So that's pretty exciting that we'll know the first time we actually burn something on another world.
Big picture, it's intelligent beings using fire on another world. That's very inspiring to think about it that way.
Yeah, it's like almost like a benchmark for humanity too. When we explore other worlds, that's one of the first ones will be, well, when do you make use of the tools that we've used on Earth, like fire, for example? And then when you ultimately have a self-sufficient colony at some point in the future, that will be another one, and it just goes out from there. So it's just a stepping stone, but it's pretty significant.
Wow. This has been so cool to speak with both of you about this experiment. I know a lot of work has gone into this, but it just to me shows the value of just those what's seemingly like minor details, like what happens when you kind of change gravity a little bit, how it can excite an entire community to really do an investigation, and it really lends to making human spaceflight successful as well. The safety is huge, whether you're going to the moon, whether you're going to Mars, right? It's very important to know how those different gravity environments, how the different composition of atmospheres, the triangle that you mentioned, Dr. Furcool, is very important. And so this has been very exciting for me to chat with both of you today. Appreciate you both, Emily and Paul. Thank you for coming on.
Well, yeah. Thank you very much.
Thanks for having us.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0J, and I feel fine.
Shuttle has cleared the tower.
Became a feast for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.
Hey, thanks for sticking around. Hope you learned something today. You can check out the latest from around the agency at nasa.gov. And you can find our full collection of episodes and all the other wonderful NASA podcasts we have at nasa.gov/podcasts. On social media, we're on the NASA Johnson Space Center pages of Facebook, X, and Instagram. If you have any questions for us or suggestions for future episodes, you can email us at nasa-houstonpodcast@mail.nasa.gov. This interview was recorded on May 9th, 2025. Our producer is Dane Turner. Audio engineers are Will Flato and Daniel Tohill. And our social media is managed by Dominique Crespo. Houston We Have a Podcast was created and is supervised by me, Gary Jordan. And of course, thanks again to Emily Johnson and Dr. Paul Furcool for taking the time to come on the show. Give us a rating and feedback on whatever platform you're listening to us on, and tell us what you think of our podcast. We'll be back next week.
3, 2, 1.
This is an official NASA podcast.